we'll study some applications of derivatives or differentiation. The first obvious application of derivatives was what is the first derivative? The first derivative. What is the meaning of the first derivative? Do you remember? What is the meaning of the first derivative? It is the rate of change. Rate of change. If I tell you, for example, that y dash at some point is, for example, is plus 100, what does that mean? What does the sign mean of the derivative? The sign of the derivative, what does it mean? Do you remember? What is the difference between this and this one? Minus 100. The sign represents if the function is increasing or decreasing. Okay? So remember, the sign indicates whether the function is increasing or decreasing. That's why when I tell y dash is plus 100, it means that at this point the function will be increasing. And here, is it increasing fast or slow? It depends. Do you consider the 100 as a big number or a small number? If we assume that this number is a big number, so this means that it is changing increasingly. It is increasing very fast. It is increasing fast. What about this? At this point when I say y dash is negative 100, it is decreasing but fast. It is decreasing very fast. It is decreasing fast. But when I say, for example, that y dash is equal to 0.1 plus 0.1, this means that the function is increasing, yes, but slowly. Yes, increasing but slowly. When I say y dash is negative 0.1, it is decreasing but slowly. Decreasing slowly. Okay? So this is the meaning of the first derivative. It is the rate of change. It has a value. This is the most important subject that you must learn in a derivative. What is the meaning of the derivative? It is the rate of change. It is the speed of change. Okay? It has a value and it has a sign. It has a value and it has a sign. So the value represents the rate itself, the speed of change itself, and the sign represents somehow the direction of the change, whether it is increasing or decreasing. Okay? So this is the first derivative. When I tell you that if S is a function of time, what is S? S is the position of some car, for example. This is S. S is the position of some car. So what is ds by dt in this case? The position of the car changes with time. For example, I can say that it is t squared plus t. It associates each time instant with a new position. Okay, so this is a description of the change of the position of the car with the time itself. I associate each second, each time instant with a different or a new position. Okay, so this is a description of the change. Now I need to specify the change itself. What is ds by dt? What does it represent physically? What is the rate of change of the position with respect to time? It is no.
Velocity.
Yes, it is the velocity. It is the velocity. It is the speed. When I say the speed or velocity, it is a more accurate. It is velocity. Speed is something somehow different. It is the rate of change of the magnitude of the position. Okay. Now this is the velocity. Velocity is the speed of change of the distance of the or the position of the car. Okay. So I may say that this is v of t. So what is v of t in this case? It will be 2t minus 1. 2t minus 1. Okay? Now, what is d2s by dt squared?
Acceleration.
Yes, and this is dv by dt. You have learned the second derivative. It is the derivative of the first derivative. So this is exactly d by dt of ds by dt. And this is the velocity, so that will be dv by dt. Okay, now this is the derivative or the rate of change of the velocity. The rate of, I can say the change or the rate of change of the velocity itself with time. This is called acceleration. Okay, it describes how velocity itself changes. Do you know, when comparing two cars, for example, they say this car can go from 0 kilometer per hour to 100 kilometers per hour in just 1 minute. Another car may go from 0 kilometers to 100 kilometers in 10 minutes. What is the difference between the two cars in this case? It is the acceleration. Yes, it is the acceleration. This has high acceleration. You have made an achievement of change in velocity in just a small time. So you have a high acceleration. Okay, the speed of change of the speed itself, of the velocity itself. Okay, but this is somehow slow. Maybe we can make it 100 minutes. Okay, this is a slow acceleration. Okay, when I tell you when does what is s of 0 in this case? S of 0 in this case, what is s of 0? It is called the initial position. At time 0. It is at time 0. What is s of 0? I will just substitute t with 0. It will be 1. So this car starts at position 1. It starts at position 1. Now I need to know in which direction this car will go. This direction or this direction. Now remember that this is the direction of s is increasing, and this is the direction that is s here is decreasing. So how to know if the car will go in this direction or that direction? We will find the velocity. Let's find the velocity. It is 2t minus 1. So at time 0, the velocity vt, it is 2t minus 1. So at time 0, what will be the velocity? It is negative 1. What does that mean?
Decreasing.
Yes, the position is decreasing. So that means that s, the new position, will be here or here?
To the left.
Yes, to the left. So it will go in this direction. Okay, how did I know that? Because the velocity is negative, so it is in the negative direction. Or it means that s is decreasing. So it will go to the negative direction. Okay. When would it change its direction again? When would the car change its direction again?
When the acceleration is
It will now just investigate it or inspect it like this. When t, for example, is equal to let's say when t is equal to 1, what will be the velocity? At t is equal to 1, the velocity will be positive 1. So at time t1, it will go in this direction again. So there is some point or some time instant where the car will change its direction. We have learned that at time 0, it was going this direction, left direction. But at time 1, it is going in the right direction. So some time in between, the car changed its direction. How could I know this time? When would it change its direction? Now let's graph this function. Let's graph this function. Let's graph this. This is v and this is time. This is a straight line. 2t minus 1. 2t minus 1, this is a straight line. When we've learned that at v is 0, at time 0, the velocity is negative 1. The velocity is negative 1, so I have this point. Also, I have another point that at t equals 1, the velocity will be positive 1. At t equals 1, the velocity will be positive 1. So I have this line represents the velocity changing with time. Now, just inspect that graph. When the time, at time 0, the velocity was negative, so it is going the left direction. And time goes on, okay, and some point the velocity became positive, so it changes direction. When is this instant happened?
When the value is changed?
It is obvious from the graph. There is some critical point for which the velocity changed its direction from going from negative to positive. What is the separating point between the two cases? At this point. At this point, when the velocity is equal to 0. That's why when you are going in this way, and you need to change your direction, you must slow down until your velocity becomes 0, then you change your direction like this. So it's some separating point for which your velocity will be 0. The point or the instant of changing your direction, it is exactly the point where which your velocity will be 0. Okay? So this is exactly that point. Can I know this point? From this is the graph. When would the velocity be 0? What is the time instant for which the velocity will be 0? So I need to solve this equation. So what is the solution?
T equals half.
Yes, t equals half. So at t equals half seconds, the car will change its direction. Okay? The car will change its direction. Then, so I can describe the movement of this car. It will go at time 0. It will go in this direction until time is equal to half. Then it will change its direction again like this. Okay? Now, if I need to find the acceleration of this car, what is the acceleration of this car? dv by dt will be
2.
Yes, it will be exactly 2, positive 2. So the acceleration is positive 2. The acceleration is positive 2, it means that the velocity is always increasing. Remember that velocity started with a negative value, then so it is increasing, the velocity is increasing, then it continued its increasing, it continued in increasing in this way. So would it change its direction again? No change in direction, because the velocity is always, it is in the positive direction, it will just keep increasing in that direction. Okay? And maybe this is not quite practical, because some way the velocity will go to infinity, and this is not practical. Okay? But it is just an example for observation. Okay? So this is a direct application of first derivatives and second derivatives. We need to know these applications, okay, in your mind. So in general, the first application that we know geometrically, let's talk geometrically now, or when studying the graph by itself. When I have some graph, what is the first derivative in the graph? At some point, what is the first derivative? It is, we know that it is the rate of change, but graphically it is the slope of tangent. It is the slope of tangent. The slope of tangent. So the top of tangent is just exactly the number that represents the rate of change, which have some physical meaning to us. But geometrically in the graph, it is the slope of the tangent. Okay? Now remember that the objective of a first derivative is to approximate a curve as if it is some infinitesimal lines, small lines like this, very small lines like this. So that's why when I need to approximate a curve around this point, what is the approximation of the curve around this point? It is just the line of the tangent, and its rate of change or its slope represents the derivative. Okay, so the derivative, what does the derivative do? It approximates the curve at a very small point as a straight line, a tiny straight line, a very tiny straight line. What is that line? It is, if you span it like this, it will just be a
single point.
A line. No, it is not a point. It is a bit of a line, a small line. Okay, a line that has a property, which is its slope. This is different from this, different from this, different from this. If you say just it is a point, now the first approximation of a curve, it is some points. But this is not enough for us. We have learned something more, which to approximate each bit of the curve as if it is a small line. Why? Because we have a new property, which is these are all different. These tiny will have different properties. What is it is different in? It is different in its slope, its change. Okay, so we are representing the curve with small or tiny straight lines. Okay, so this is the first derivative. What about the second derivative? Now just remember that the straight line, what is the slope, what is the derivative of straight line? This is a straight line, ax plus b. This is a straight line, or mx plus b. This is a straight line. What is the derivative of this line, y dash? What is y dash in this case?
M.
Yes, it is m. So the curve that has a constant first derivative is a straight line. What is the curve that has a constant second derivative? Now we need to know what is the meaning of the second derivative. What is the curve that has a constant second derivative? Do you know it? Let's take, for example, y is equal to ax squared plus bx plus c. Let's find its first derivative. What is the first derivative? It will be y dash will be 2ax plus b. What is the second derivative? 2a. So this is a constant. So the curve that has a constant second derivative is just this is called a second degree polynomial. It is called parabola. This is a more generic name, which is called a parabola. It is called a parabola. The parabola, or a standard parabola looks like this. A standard parabola looks like this. Okay, this is y is equal to x squared. The y dash is 2x and y double dash is equal to 2. So this is positive 2. This is a positive 2 second derivative. This represents a positive 2 second derivative, a constant positive second derivative. What about this? If it was like this is called minus x squared. This is called negative x squared. This is called negative x squared. So this is negative x squared. When you find the y double dash, it will be negative 2. So this represents a constant second derivative equal to negative 2. Just as a constant derivative, you may approximate the line with tiny lines. We will also represent the curve with tiny parabolas like these. So The line was only capable of finding its direction of change, a slope, only a slope. But a second derivative represents something new, a new concept, which is the concavity. This little part may be looking downward like this, or it may be looking upward like this. This little part in the curve, it may be looking down or may be looking up. What determines if it's looking down or looking up?
Sine.
It is the sign of the second derivative. Why? Because the second derivative, it is represented as a parabola. So what does the second derivative do? It approximates the curve with tiny parabolas, as if you are looking to the curve, as if it is like this. Parabolas, just small or tiny parabolas. You are putting a new property in addition to the slope of the direction of change, or the direction of change, or the slope of tangent. You are finding another property, whether it is looking upward or looking downward. That second property is determined by the second derivative. Why? Because the second derivative represents a parabola. A constant second derivative is represented by a parabola. Okay? And that's why we determine, in general, we determine it is called the concavity. It is called concavity. It is called concavity of the curve. If I have, for example, a curve like this, this curve has a negative second derivative in this part. So the second derivative, in this case, f dot dash, it will be negative in this case. It is looking down. This is called concave down. Concave down in this interval. What about this interval? For this interval, the function is looking up. It is called concave up. Concave up. And the second derivative in this case will be positive, yes. In this case, in this part of the curve, it will be positive. Now let's check this example. Determine whether the graph of f of x equal to x minus 1 all cubed plus 1 is concave up or down. How to determine if a function is concave up or down? We find the second derivative. So let's find the second derivative. First, the first derivative first. It will be 3x minus 1 all squared. Then we find the second derivative. It will be 6x minus 1. Now, I need to study when this function is greater than 0 and when it is less than 0. How do you know when it is greater than 0 or less than 0? Remember? In general, we find that maybe this is an easy inequality. But remember that we have studied in the problems in finding the domain how to know the sign of the function. So we will study this function. We will find its sign when it is positive and when it is negative. How? We find, do you remember? We find the zeros and poles of this function. The zeros and poles of this function. What are the zeros of this function? It is just 1, x equal to 1. The zero, it makes what makes the denominator equal to 0. What are the poles? They are the points that make the denominator equal to 0. So, do you have a denominator in this case? No, we don't have denominator, so we don't have poles. Anyway, we should have taken the zeros and poles and depict them on the number line. We only have x equal to 1. We only have x equal to 1. So we'll study the sign of that function. Remember that we are studying this function. We'll study the sign of this function around this point, or around the zeros and the poles. We just take a point in this part and take a point in this part. Any point, any random point, but make it easy. Just take 0 for in this case and take 2, for example, in this case. When you take 0, we'll substitute with 0, it will just be negative. We just need the sign, so it will be negative 6. When I substitute with 2, 2 minus 1 will be positive. So what does that mean? It means that the function is looking down in this part, then looking up in this part. We say that it is concave. It is concave up in which interval? From 1. It is concave up from 1 to infinity. Concave up from 1 to infinity, and concave down from yes, from negative infinity to 1, open. Okay? Now, whenever we have a function that the second derivative changes its sign or changes its direction from concave up to concave down, or the opposite, from concave down to concave up, we call this point an inflection point, if it is in the domain. So if this function is in the domain of the function, so this point will be called an inflection point. Why? Because there is a change in the sign of the second derivative about it, around this point. Okay? So this is called an inflection point. Remember that an inflection point must be in the domain. If it is not in the domain, it cannot be considered as an inflection point. Okay? So that's how we can determine when the function is concave up or concave down. Okay? Can I know when this function is increasing or decreasing? How do we determine if the function is increasing or decreasing?
It is going from positive, it is decreasing.
Do determine the increasing or decreasing property from the first derivative or the function of self, or the first derivative or the second derivative? From the first derivative, yes. So we know whether a function is increasing or decreasing from the first derivative. So how to know if this function is increasing or decreasing? I just study this first derivative. I need to know when it is greater than 0 and when it is less than 0. And this is an inequality. So I have this inequality, or x squared. I need to know when it is greater than 0 and when it is less than 0. How to study an inequality like this, or how to study the sign of the function? Yes, we find the 0 and we find only one 0, which is 1, and no poles. Then we study the sign about it, so that will be positive and positive. What do you expect from this function, or what do you deduce from these two signs?
The slope going up.
Yes, it is increasing, then again after 1 it would be also increasing. Yes, and if you graph this function, you can graph it by knowing the transformations of functions that you have learned. It will just be a function like this. A function like this. You know the graph of x cubed, it is just like this, and it is just shifted, horizontal shift and vertical shift. Okay? It is, the function is increasing. Then there is this inflection point. Inflection point, it means that the function is changing its, whether it was looking down, then it is now looking up. Okay, so it was first looking down, concave down, then it is looking up in this way. But it is always increasing. This function is always increasing. Okay? We will make another application out of this, which is finding a maximum and minimum of a function. Maximum and minimum of the function. When does how do we find a maximum or a minimum of some function? A minimum, or these are called local minimum or local maximum. This is local maximum. Why it is local? Local because it has a value that is greater from its neighborhood, the points which are just beside it. This is called a local minimum. Local minimum. This is called a local maximum. This is called a local minimum. Okay, so if I continue this curve like this, now for this curve we have seen the local maximum and local minimums. Can you determine the global maximum and global minimum, or sometimes called absolute maximum, absolute minimum? What is the term global? It is the maximum of the function itself, of the whole function. These are local. Why it is local? Because this point is a maximum with respect to its just neighboring points, just the point beside it. It is a maximum just with respect to its neighborhood, and this is a minimum with respect to its neighborhood. This is a maximum, and so on. But what is a global maximum? For example, this we have. This level, for example, is just greater than this one. So I have this point will be my global maximum of the function. Global maximum of the function. Okay? This point is the global maximum of the function. What is the global minimum of this function?
The last one?
It is this point. So that's why global maximum and minimum, it mustn't be, or it is not a must to be a local maximum or local minimum. It just may be one of the boundaries. So a global maximum or global minimum, it may be a local maximum or local minimum. It may be local maximum or local minimum, or it may be the boundaries of the function. These are the boundaries. Okay? Now remember, a maximum point must be in the domain. For example, if I have this function like this, is this a maximum point? No. Is this a local maximum? No, it is not a local maximum. It may be called a supremum. There is another term to describe this. It is called supremum, not a maximum. But for it to be a maximum, we will not study this. This is just for your information. But this point, it is out of my domain, so it cannot be a maximum. So this function doesn't have a maximum, or doesn't have a local maximum. This function doesn't have a local maximum. Okay? This function doesn't have a local maximum. Okay, so a maximum point must be in the domain. It must be in the domain of to be a local maximum or to be a local minimum. Okay? So let's now learn how to find. We need to find local maximum, local minimum of some function, and we need to find the absolute maximum or absolute minimum, or the global maximum or the global minimum. Okay? We need to check how to find all of this. Now, how to find a local maximum or local minimum? There is a behavior of the function associated with a local maximum. The function increases, then it decreasing. Yes? It increases for a point to be a local maximum, it increases, then decreases. And the point for which there is a separation, it is exactly my local maximum. Okay? Now, how to know if the function is increasing then decreasing? We know that from the first derivative. Yes, we know that from the first derivative. So that's why we study the sign to find local maximum or local minimum. We study the sign of the first derivative. For example, if I have this function, if I have y is equal to x squared e power x, I need to know the local maximum and local minimum and study the increasing or decreasing, the function, if it is increasing or decreasing. We find the first derivative, product rule, first, and derivative of the second, then derivative of second times the first. That will be, I can take e power x common factor, that will be x squared plus 2x. So I have this function, okay? Now, I need to study this function whether when it is greater than 0 or less than 0. We need to study the sign of this function. How to study this? The sign of this function, we find the zeros and poles. The zeros and poles. When it is equal to 0 and when the denominator goes to 0. Okay? When the denominator equal to 0, I have two cases, x squared plus 2x equals 0 or e power x equal to 0. Can e power x be equal to 0? No. It just is equal to 0 maybe in negative infinity, but in general it is rejected. So in this case we have x plus 2 equal to 0, and that will be x equals 0 and x equals negative 2. So we have two zeros, which is 0 and negative 2. We have negative 2 and 0.
Just point. Just point.
Yes. Then we have no poles. We have no poles for this function, okay? Now we test some points, for example negative 3, negative 1 and 1. This exponential is always positive, so I mustn't put it in my consideration. It is always positive, so I don't need to check it every time. I need just to look at this function, or maybe this factorized one is more suitable. Why? Because for this one I put negative. This is negative, and negative 3 plus 2, it will be negative 3 plus 2 will be negative. Negative times negative will be positive, so that will be positive. For negative 1, this will be negative, and this will be 2 minus 1 will be positive. So negative times positive will be negative. For positive 1, this will be positive, and that will be positive, so all will be positive like this. So what is the behavior of this function? It is increasing, then decreasing, then increasing again. Okay? It is increasing, then decreasing, then increasing again. If this point is in the domain of the function, I will call it a local maximum. If this point is in the domain of the function, I will call it a local maximum. If this point is in the domain, are these 2 points in the domain?
No.
This is the function. Are these in the domain of the function? Yes, this function, its domain is R. So negative 2 is in the domain and 0 is in the domain. Okay? So these 2 points are in the domain. So this point is called a local maximum. And this point is called a local minimum. Okay? I may graph this function. This function will just be something like this. At negative 2 and 0, it will be like this. It is increasing, then at negative 2 it became decreasing, then it became increasing again. Okay? Maybe at negative infinity, do you know what is negative infinity of this? We have learned the limits. Negative infinity of this, x squared e power x. This is exactly x squared over e power minus x. Limit x going to negative infinity. If you differentiate, it will be infinity over infinity. This will be infinity over infinity. So it will be 2x over e power infinity minus e minus x. Differentiate again, it will be e over plus e minus x. So it will be, when you put this, it will be 0. So that means that this function will go to 0 like this. I will have a horizontal asymptote. I will have a horizontal asymptote when going to negative infinity. Negative infinity will have a horizontal asymptote like this. You need to know how to find this limit. You have learned L'Hopital, and you need to know to practice how to find this limit. I just applied L'Hopital 2 times. Okay? Now, can I know the global maximum or the global minimum? The global maximum or the global minimum. How to know the global maximum or global minimum? We just, as putting a term for this, when finding when is this function equal to 0, or the zeros and the poles of this function are called critical points. Okay? The zeros and poles of this function of the derivative, when the derivative is equal to 0 or equal to infinity, which makes the derivative non-existent, the derivative not exist, is called critical points. Okay? When the derivative is equal to 0, or the denominator is equal to 0, or sometimes when any point for which the derivative does not exist. What are examples of a function of a point that a function doesn't exist? For example, this point, the derivative is not exist. A known function for the absolute x. At 0, the derivative at x equals 0 is not existent. Does not exist. F dash does not exist. Why? Whenever you have a derivative on one side equal to some number and a derivative in the second line equal to slope of tangent. We have here two slope of tangent, a slope of tangent and a slope of tangent. Here we have a slope of tangent, another slope of tangent around that point. So if the tangents are not smooth, the first derivative will not be existent. Okay? So it is just a point of حاجة زي مدببة كده. مش عارف بالإنجليزي اسمها إيه مدببة. A sharp, not smooth point. It is a sharp point like this. Okay? Any sharp point like this, the derivative is not existent. So any point for which the first derivative is 0 or infinity. What are the poles? Poles are the function where the function is equal to infinity. So whenever the first derivative is equal to 0 or equal to infinity by the poles, or not existent, these points are called critical points. And these are exactly the points for which a sign may change. A sign of the first derivative may change. Okay? So these are the points that we put on the number line and we study about them. So what are my steps to find the local maximum or local minimum? We find first the critical points. What are the critical points? Which are the zeros and poles and maybe the functions for which the function is not, the derivative is not existent. So these are called the critical points. We find them, then we put them on the number line. Then we study the sign about them, around them. Okay? So this is how to find local maximum and local minimum. Now, how to find the global maximum and global minimum? After to find the global, we don't have to find the local maximum and local minimum. We just need to find the critical points. We have learned that global maximum and global minimum may be a critical point, or it may be a boundary point. It may be either this or this. So that's why to know a critical point, to know a global maximum or to find the global maximum or the global minimum, we just find the critical points and we find the boundaries. Here in this function, the boundaries are infinity and negative infinity. So we'll just take it out of my consideration. Infinity and negative infinity, we take it out of my consideration. Okay? We just have here the critical points. What do? We just take every point and find its function. every critical point, which are 0 and -1, these are my critical points in this case. We find the function, and if we no, maybe we have the infinity and f of minus infinity. We just put it in our consideration. These are the boundaries. F of 0 is equal to 0. F of -2 is equal to 4 power 4 e power -2. This is some number. F of infinity, we'll find it infinity. F of minus infinity, we'll find it to be 0. What is the least value of all of these values? It is 0. So this is the global minimum. Global minimum is equal to 0. What is the maximum value? The maximum value is infinity. So it has no, when the maximum value is positive infinity, we say that we have no maximum. Okay? We have no maximum. Okay, let's check another example. Give me this function, y is equal to x plus 4 over x plus 1. And he's telling me find local extrema. Find local extrema. Find local extrema. How to find local extrema? What is local extrema? Local extrema, it is just a short abbreviation for maximum or minimum. Okay, the maximum and minimum are called extreme points. So we call it extremas. So we'll find the first derivative, which is 1 minus 4 over x plus 1 all squared. I just need to find what are the poles and zeros of this function, or when is the derivative not existent. So we find the critical points for which y dash, we have two cases. Y dash is equal to 0, or y dash is equal to infinity, or not exists. Not exists, maybe two cases, either infinity or poles, or it may be not exist a sharp point, or it is called a cusp. Okay, let's check. When is this function equal to 0? When is y dash equal to 0? We need to find the critical points first. So we just put 1 minus 4 x plus 1 whole squared equal to 0, which is 4 over x plus 1 whole squared equal to 1, which is x plus 1 whole squared equals to 4, for which x plus 1 equal to plus or minus 2, for which x will be equal to what? It will be equal to negative 1 or negative 3. 1 or negative 3. Okay, so these are the zeros of the function, the zeros of y dash, We need to study the sign of y dash, so we study the zero. So we have 1 and negative 3 and 1. Okay, any other points for which y dash is not existent? Yes. Do you have a pole in this case? Yes, we have a pole. For which here we have a denominator. Whenever we have a denominator, so we'll have a pole. So what makes this denominator equal to 0? Which is x equal negative 1. So we have a pole x equal negative 1. So we'll put x equal negative 1 in this case. This is a pole. Okay? Do you have sharp points or cusp points? These are obvious from maybe absolute or functions. It is obvious from other functions when we describe a function like this. We tell you, for example, y is equal to 2x plus 1 at x greater than -1 and x from -1 it will be 3x minus 2. When you have branches, when you describe a function as branches, you may have a cusp or a sharp point in the separating point at this -1 point. How do we know that? We find the derivative at this and the derivative for each branch. We find the derivative at each branch. If they are not equal, then we'll have a sharp point or a cusp point. Okay? So here we don't have no branches for this function, so we don't have a function like this. So what we'll do now, we'll just study the sign of the function. We check some points: -4, -2, 0, and 2. For -4, this is squared. -4, it will be -3. I think this will be positive. This will be positive. -2, this -1. 1 minus 4, this will be negative in this case. With 0, that will be 1 minus 4, it will be again negative. And for 2, it will be 2 plus 4, 4 squared. 4 squared, 1 minus 1. What is 2, 3? 3 squared, this is 9. This will be a fraction, 4 over 9. It will be a fraction, so that will be positive. So this function is increasing, then decreasing, then continue decreasing, then increasing again. Okay? Now, if it was decreasing, then increasing, would it be a local maximum, a local minimum? No, remember, for a function to be, or a point to be a local maximum or local minimum, it must be in the domain of the function. This is not in the domain of the function. And that's why I put it in red, because it is not in the domain of the function. So it cannot be a local maximum or local minimum. It cannot be a local maximum or a local minimum. Okay? But anyway, the function here, the f dash didn't change its sign about the -1. What about the other points? What about this -3? It was increasing, then afterwards it is decreasing. So this point is a local maximum. But at first you must determine, or you must check if this point in the domain of the function. Yes. What is the domain of this function? It is just R, all R except -1. This is the only problem in the denominator, is the only problem in this function. So -3 is in, this is green, I will put the green, and this is 1 also, it is green. Okay? So that's why that one will be a local minimum. Yes. So these are the local extremas of this function. These are the local extremas of this function. Let's check this. Consider y is equal to y equal -x plus absolute x minus 2. Now this function has an absolute. How I would describe it? I would just, yes, I would write it. Do you remember how to write an absolute? Absolute x or absolute something? Absolute something is the positive of that when that is positive, or negative that when that is negative. Okay? So what is absolute x minus 2? It will just be x minus 2 when x minus 2 greater than 0, it will, or x greater than 2, and this is x greater than 2, it will be 2 minus x, the negative of that expression. So that y will be, I will rewrite it as e minus x plus x minus 2 when x is greater than 2, and e minus x plus 2 minus x when x is less than 2. So I've rewritten it as this expression. Now I need to find the local extremes. The local extremes of this function. Hence find global extremes, local extremes, and the local extremes, the local and global, hence find the range. Okay, let's check. To find the local extrema, we find the first derivative. What is the first derivative? It will be minus. I just make the derivative of each branch. Minus 1. X greater than 2 and x less than 2. Now I need to know when is this function equal to 0 and when the derivative is not existent. When it is equal to 0, I check each branch when is equal to 0. Let's check this branch. Minus e minus x plus 1 equal to 0. This means that e minus x is equal to 1. This means minus x is equal to, when I take ln both sides, it will be 0 and this will be x equal to 0. This is the point for which this branch is equal to 0. Is this in the domain of the branch? Is x equal to 0 is in the domain of the branch? Remember that this is the domain of a branch, of this first branch. X must be greater than 2. Is that solution, x equals 0, is in the domain of the branch? No, it is out of the domain, so this is rejected. So let's check the other branch. I will check minus e minus x minus 1 equal to 0. So e power minus x equal to negative 1, and this is rejected at first. Why? Because an exponential is never negative. An exponential is never negative. So this y dash is never equal to 0. But I still need to find when is y dash going to infinity, or if it has a pole, or it is not existent. It doesn't have a pole, it is obvious that it doesn't have a pole. Okay, it is obvious that it doesn't have a pole. But it may have, we have two branches, so it may have a point for which the derivative is not existent. So what I do here, I just find the derivative at the separating point. The separating point. This is a potential point for which the separation point is a potential point for which the derivative may not exist. So I find the derivative y dash at 2 plus. 2 plus, it is that branch. Just the number after 2. At that branch, let's find the derivative. It will be e minus 2 plus 1. Y dash 2 minus, which is the derivative from that branch, it will be minus e minus 2 but minus 1. Are these two equal? No. So y dash is not existent. Is not existent at x equal, yes, we have a sharp point here. We have a sharp point. A sharp point. Is this a critical point? Yes, it is a critical point. It is a critical point. Okay? So, how to study the derivative? We just put the critical points. So, we have here 2. Is 2 in the domain of the function? Yes, it is in the domain is R. The domain of this function is R. حد معملها دي؟ Now we study about the critical points. This 2, yes, this 2 is, I will make it green, so we know that it is in the domain of the function. Now we study, remember, this is y dash. Y dash is equal to e minus x, minus e minus x. I'll just take it. This is y dash. This is y dash. Okay, this is y dash. Now I need to study the sign about this critical point. Take for example 0 in this case, and take for example 3. When you check 0, 0 is belonging to which branch? The first branch or the second branch? Do I substitute the 0 in the first branch or the second branch?
Second.
In the second branch, yes. So it is e minus 0, e power 0 minus 1, that will be negative 1, which will be negative 2, which will be negative. For 3, 3 is belonging to the first branch, so it will be e power negative 3 plus 1. E power negative 3 is the fraction. It is 1 over e power 3 plus 1. 1 minus, it is 1 minus a fraction, which will be a positive. Yes, a positive value. So that would I don't need the exact value of it. I just need its sign. So this function will be decreasing than increasing. Now this 2 is belonging to the domain of the function. So that will be a local minimum. That point will be a local minimum. That point will be a local minimum. Okay? So we just have one local minimum for this function. Now, I need to check the global extrema. Global extrema. How to check the global extrema? We find the critical points, which is only one critical point, which is 2, and we find the boundaries. What are the boundaries of this function? It is infinity and negative infinity. Infinity and negative infinity. So this is the function e minus x plus absolute x minus 2. F of 2 is e power minus 2. I just substituted here. Now remember, for finding a global extrema, we just take the critical points, these critical points, and substitute in the original function. Substitute in the original function. And check the values of, and take the boundaries, the critical points and the boundaries, and check the values. What is f of infinity? It is e power minus infinity plus infinity minus 2. So that will be 0, 0 plus infinity, which will just be infinity. F of minus infinity, it will be e power minus infinity, it will be e plus infinity, and plus minus infinity minus 2, it will be infinity plus infinity, which will just be infinity. Okay? So what is the maximum of this function? There is no maximum. Why? When the maximum is infinity, we call it there is no maximum. Okay? So maximum is equal to infinity, we call it no maximum. What is the minimum of this function? The global. This is the global. What is the global minimum? It is just this value. So the global minimum is e power minus 2. And it happens, the minimum itself is e power negative 2. It occurs at x equals, what is the x that makes yes, it will be x equal to 2. So this is the point for which the function gets its value of its minimum value. Okay? Now, this function is a continuous function, so the range of a continuous function is just, if I have a continuous function like this, what is the range of this continuous function? It is just the interval between the global maximum and the global minimum. Yes, so we have in this case, what is the range? What is the range for this continuous function? But as a condition for this to be a continuous function, the range, you can just make it at the maximum and minimum, in between the global minimum and the global maximum, if the function is a continuous function. Now, for this case, it will just be from e power negative 2 to infinity. This is the range of this function. And this is a new way to find the range of the function, different from the other methods that we have learned before. Okay? Let's check this function. It's telling me here, find the absolute extreme. F of x, 1/3 x cubed minus 4x plus 5 over the interval 1, 4. He needs here just only the absolute extrema. Absolute extrema. Absolute extrema are just the global extrema. Global extrema. So f dash, we find the f dash, which will be x squared minus 4x. I will just check when f dash is equal to 0 and when it is not exist. For it to not exist, when we have poles or sharp points. We don't have sharp points. Also, we don't have poles. Only maybe this will be equal to 0. So x squared minus 4x equal to 0. X minus 4 is equal to 0. X equal to 0. So here we just have zeros. So these are the only critical points. These are the only critical points. Okay. Do we need to check the sign? In this case, no. When you are checking just only the absolute extrema, you just take the critical points that you have found. So we'll check f of 0 and check f of 4 and check the boundaries. What are the boundaries in this case? 1 and 4. So we'll check 1 and we'll check 4. Now, is this an acceptable for my domain? Is this an acceptable critical point? Remember, the domain of this function is from 1 to 4. Do I accept 0? No, I will not accept 0. So I will just take this out of my test. Okay? I'll just take it out of my test. So I'll just check these 4 points. Those 3 points. It is only 2 points. Yes, this is just equal to this one. Because one of the critical points is just the boundary. It's just the boundary. So I'll just find. No, maybe I'm wrong in this. There's something wrong in this. Yes, this is 4. Yes, this is 4. This is 4 only. So that will be 4, and that will be x will be equal to. Yes, x will be 2 or negative 2. Now here I will just reject the negative 2. It is out of my domain. Okay, I'll just take the 2. So I will have here the only critical point is 2. And the boundaries will be 1 and 4. I'll just find the f of the values of, I'll just put the 2 in and the 1 in this function. That will be f of 2 will just be negative 1/3. F of 1 will be 4 over 3, and f of 4 will just be 31 over 3. It is obvious that this is the maximum value and this is the minimum value. This is the maximum value, so we have found the critical, and this is a continuous function, so we may say that the range is from negative 1/3 to 31 over 3. Okay, the range in this case it will be like this. Okay, we have learned how to find the first derivative, the local maximum. Let's return again to the local extreme. We have learned to find a local extrema by checking the first derivative, the sign of the first derivative. Okay, another test, it is called the second derivative test. This is called the first derivative test. We have another test which is called second derivative test. Maybe sometimes easier. You just check the second derivative at the critical point. You check the second derivative, at the critical point. Why? Because it is obvious, if you have this function, this is a local maximum. This point is a local maximum. Okay? If it is increasing then decreasing, then it must be concave. It will be looking down or up. It is increasing then decreasing. It is a local maximum. So it will be looking down, which is concave down, which has a second derivative will be So if the second derivative is when concave down, the second derivative is negative, it means that this is a local maximum. And if the second derivative is positive, which is concave up, it will be a local minimum. So this is called the second derivative test, and it is easier from checking the signs about checking some point, random point, and so on. But it has disadvantage if you may have a point for which f double dash is equal to 0. In this case, the test failed, and you may return to the check by the first derivative test again. Okay, so you may have a function for which the second derivative is equal to 0, and it may be a local maximum or a local minimum. Okay, so you
if the test failed in the second derivative, you go back to the first derivative. If you try the second derivative and it failed, you go back to the first derivative.
Yes, we go back to the first derivative test, which is checking the signs of about the critical point. Okay. If I have this example, y is equal to 18x minus 2 over 3x cubed. Find the local extrema, but he's telling me using the second derivative test. We just find y dash, it will be equal to 18 minus 2x squared. We find y double dash, which is equal to minus 4x. We find the critical points from this. The critical points will be 18 minus 2x squared. We only have the zeros of this function, so that will be 18 minus equal to 2x squared, which is x squared equal to 9, for which x is equal to plus or minus 3. So we have two critical points. So what would I do? I would just take each one. I will check y double dash at x equal positive 3 and y double dash at x equal negative 3. I will check the values. Instead of checking the sign about the plus or minus 3, I will just check the second derivative. I will just check the second derivative. That will be negative 12, which is a negative value, and that will be a positive value, which is 12. This is positive 12. So that means that at x equal 3, this is a local. When you have a negative, so that is looking down, it is a local maximum. So, and for this point, it will be a local. When the second derivative is positive, looking up, so this is a local minimum. Okay, just from the second derivative, we have learned that, or we have determined the local maximum and the local minimum. So let's check the last example. If we have y is equal to 6x power 4 minus 8x cubed plus 1, we'll find y dash is equal to 24x cubed minus 24x squared. Y double dash is equal to 72x squared minus 48x. We find the critical points for which this is only equal to 0. The critical points will happen at y dash equal to 0, x cubed, 24x cubed equal to 24x squared, or minus equal to 0, 24, so x cubed minus x squared equal to 0, x squared common, x minus 1, so that will be 0 and 1. We have two critical points at 0 and 1. So I'll just take each of these values and I will check y double dash at x equals 0, y double dash at x equals 1. We'll check these two values. Y double dash at x equals 0, it will be 0. Y double dash at x equals 1, it will be a positive value. So this is a local minimum. Okay, but what about the 0? test fail. How would I know the classification of the function at x equals 0? I will just return to yes, the first derivative test. So I check the 0, I will check the derivative, right to the derivative, and second to the derivative, right and left to the derivative. So I check, for example, -1 and yes, -1 and 1, for example, and I substitute in the first derivative. That will be maybe this is 24 times all of this. 24 is positive, so that will be positive, -1, it will be negative, positive 1. No, I don't. I mustn't choose 1. Why? Because 1 is one of the critical points. I need to check another point, which is half, for example, half. So half will be positive and negative, so it will be negative again. So what about 0? The 0 point, is it a local? The function is decreasing, then decreasing again. Is it a local maximum or minimum? No, it is not a local maximum, neither a local minimum. Okay, enough for today.